So multiplication becomes addition. And then guess what division becomes? Subtraction. That's right. M over N. So if that's what we're taking the log of some division problem, it's going to be log of the top minus log of the bottom. Multiplication becomes addition. Division becomes subtraction. And that'll help us as we go along here doing some things. Log of some base, and then if we have m to the r. Okay, so it's a different base. This one looks a lot like number 4 did, except for the base and then this base right here are not the same. Because they're not the same, they can't cancel each other out. But what can happen is this power property that pulls the exponent down to the front. So that r goes down to the front. That's what that does. That exponent can move down to the front. And then we're undoing multiplication instead of undoing an exponent. So when we go to solve equations, this makes things a lot easier because you're not having to undo an exponent, you're just undoing multiplication, which is a lot easier to divide by something than it is to take whatever root that you're dealing with there. And then get into the natural log of E. That's another one of those simplifying. The natural log of E is log base E of E, so that cancels out and makes 1. And then last one is the exponentiation. The natural log X, natural log of A is going to be A to the X. You don't use these two quite as often as you do the others, but we're going to try to use them some as we go along here, just so we get a little practice with those logarithmic properties. So make sure you're kind of working on learning those things. It's basically if you learn the concept that multiplication becomes addition and division becomes subtraction, and then exponents come down to the front, then it's going to help you. If you'll learn those things, then it'll help when we're doing some stuff. So what we're going to work on first is write the log as a sum or difference. And you'll hear me say this every time because this is the way I've always taught it, as expanding. So what we're going to start with is a logarithm, and we'll just do base 4 because it doesn't matter what base it is. And we're going to take that and try to break it into as many pieces as legally possible out of that. Because what breaking it apart does is it helps us to learn the properties, and then we will take some that are broken apart already and condense them down. The condensing down is really what you need to be able to solve equations later on. But learning the properties is best learned by going backwards and splitting them out, okay? So big thing to see right here is what's going on between the x and the square root of x squared plus 1. They're multiplying together, right? And written like that. So I can take that and split it apart as a log base 4 of x plus log base 4 of the square root of x squared plus 1. So I've taken this multiplication problem because they're multiplying x times the square root of this jump. They're multiplying together. The first step says, oh, if it's multiplication, I can split it apart into addition. And I can split it like that. Well, this one, is there anything else going on with that? There's not any exponents. There's not any other operation going on with this one piece right here. So it's not going to do anything. But this one has that square root on it. And what you've got to remember here is that square roots are the same thing as exponents. That the square root of x squared plus 1 can be written as that to the 1/2 power. Square roots is the 1/2 power. Cubed roots would be the 1/3 power. 1/3, 3 right there. Fourth roots would be the 1/4 power, that sort of thing. So roots can be broken into exponents. Now that opens up using the exponent property, which is number 7 there. If it's got an exponent up there, I can pull it down to the front, and that'll give us log base 4 of x plus 1/2 log base 4 of x squared plus 1. And once I get there, that's as far as I can go. Because I don't have a rule that breaks apart the log of addition. I've got rules that break apart laws of multiplication, logs of division, but not logs of addition or subtraction. So that can't be broken apart because it's got addition. All right. So that's the first example. Let's do several more here. Kind of catch on to what's going on here. Natural log x squared over x minus 1 to the 3rd power. So a big fraction in there. So a big fraction in there tells us what operation is going on. Addition, multiplication, subtraction, division. Which one of those does the fraction indicate? Division. So division with logarithms turns into subtraction. So we're going to start by subtracting. So we're going to take natural log of x squared minus natural log of x minus 1 cubed. Just like that. So we're splitting that apart into a subtraction problem. And then we're going to look at it and see if we break it apart any further. I see an exponent on that x, so that says, hey, I can pop that down to the front. That'll be 2 natural log of x. This 3 will do the same thing. And then you just leave whatever that exponent was on inside of the log. And there is taking that one logarithm and rewriting it as a sum or a difference. Just be a difference because it's subtraction. Okay? We're using those properties to try to do that. It just takes a little maneuvering. Let's try this one. Log base 5 of the square root of x squared plus 1 over x cubed x plus 1 to the 4th. A lot going on with this one. A lot going on, but what's the big thing that's happening? Division. The big fraction says that this is division. So I'm going to split it apart with the division part first. Top minus bottom. X cubed x plus 1/4. Okay, so now how can let's just work with this first one. What does the square root turn into? A half power. So where can that 1/2 go? To the front. So I'm going to pull that out to the front as a 1/2 log base 5 of x squared plus 1. And then this one has a little bit more going on. How many pieces are inside of that log? 2 of them. And what's going on with those 2? They're multiplying, which we know can turn into addition. So we really have log base 5 of x to the 3rd plus log base 5 of x plus 1 to the 4th. Notice that I put all of that in parentheses because that, I'm subtracting that entire part. Now, what can I do with those to make them a little bit more expanded. Yeah, put those exponents in the front. Log base 5, x squared plus 1 minus 3 log base 5 of x minus 4 log base 5 of x plus 1. Why did I put a minus on both of them that time? Yeah, it's like a distributed property. That's exactly it. That I'm distributing this minus sign to both of those because they're subtracting on both of that. We started out by subtracting this whole piece up here, and then when we split that apart, we're really subtracting all of that. So when I did that last step, I just went ahead and distributed the minus sign to both of those to be the fully expanded form of that. Okay. So anything you see when we go to do the condensing part, anything that's positive, you know, is going to go up in a numerator. Anything with a minus sign in the front of it's going to be in the denominator of a fraction type situation is what that's going to kind of helps us to see what's going on. So let's try to do some condensing of those. So write as a single log, and in parentheses you'll hear me say condense. You condense something, you make it smaller. So we're going to take a logarithm, log base 3 of 7 plus 4 log base 3 of x. And let's try to condense that into one single logarithm. We're trying to undo the expansion that happened. Yeah, good job. This 4 going to hop up here as an exponent on the x. So we really have log base 3 of 7 log base 3 x to the 4th. And I'm writing out every single step here. As you're working these, I would assume that most of us are going to do more than one step at a time. But so I'm trying to just write out every step so we see what's happening. Now what? Addition becomes what? That's right. Addition becomes multiplication. So this is going to be log base 3 of 7 times x to the 4th. And there's nothing else to condense. That's one term. It's got it down to one single logarithm. The exponent property, pop that exponent back up to the top, and then the addition became multiplication, and we were able to get that into a single logarithm. As we get into solving equations here in just a little bit, we'll see, hey, that allows us to get rid of the logarithms, which is the point in doing it. Let's take 2/3 natural log of x minus natural log of x squared minus 1. What could you do to this one to condense it into one single logarithm? Okay, so 2/3 pops up there. Yeah, since it's subtraction, the x squared minus 1 is going to end up going on the bottom. Now, we could take this a little bit further and kind of undo that x to the 2/3 if we wanted to rewrite that with roots. Since it's a 3 as the denominator, that means it's a what root? Cubed root, yeah. So the cubed root of x squared is what that really is. And sometimes you'll see the answer written like it is here in the blue. Sometimes you'll see it this other way. Both are equally correct, and it would just kind of depend on, what you were going to do next to solve the problem, to which way you'd want it. I actually like this way better, but sometimes you're going to see the answer choices on quizzes and tests but either way there. So be able to bounce back and forth between those two. But both of those are equally correct. for that problem. Again, I like the way in blue. That's how if I'm doing short answer quizzes and things, that's how I like them written. Because I like fraction exponents better. All right, let's do this one. One that's a little bit bigger. So 3 log base 5 of x plus log base 5 of 6 plus log base 5 of x squared plus 1 minus log base 5 of x minus 3. Really a lot more stuff going on, but because they're all the same log base, we should be able to condense this into one single logarithm so that we can have one thing to undo. Yeah, sure. Is it? Would it be? What's going on between those two? It's multiplying by 6 because that's addition, right? And addition becomes multiplication. What else is getting multiplied? That x squared plus 1, it also get multiplied. What's the only thing you were dividing by? The x minus 3. Because that x minus 3 has a minus sign in front of it, and I just highlighted that and you can't see it. Because that x minus 1, or x minus 3, excuse me, has a minus sign in front of it, we know that's the piece that gets divided by. So we're going to do log base 5, x to the third, and then it's multiplied by 6, and then that's multiplied by x squared plus 1, and then all of that is divided by the x minus 3. Condensing down, that ends up being the final piece there. Not bad, not bad. Try this one. 3 log base 10 of x plus 2 log base 10 of x plus 5 minus log base 10 of 12 minus 3 log base 10 of x minus 2. And remember, if it's log base 10, they don't have to write that 10 there. It's just understood to be there. So that's a plain log. We know it's log base 10. So how many pieces are multiplied and how many pieces are divided? Yeah, we got 2 that have a positive sign on them, and then 2 that have minus signs in front of them. So we know that these 2 are the ones that are going to be divided with. All right, so the top part there, log base 10 of what? X to the third times what? Yeah, good job. Really is just that. Now, we know the ones with the minus sign are going to be divided, but there's 2 of them. So what do they both do in the denominator? What do they do with each other? Since there's more than one of them. Because if it was just if it didn't have this part, we would just put the 12 under there and we'd be done, right? But since it has that extra piece, what do the 12 and that extra piece both do? Because they both have a minus sign. So they're both going to be in the denominator, but what's going on between them? Subtraction indicates that they're going to be divided by. If both of them are being divided by, you're going to multiply them together in the denominator. Not x minus 5, but x minus 2 cubed. The idea is that if you factored out the negative, you would have log base 10 of 12 plus 3 log base 10 of x minus 2.
means division, but two subtract, like two things being subtracted means multiplication.
In the bottom.
In the denominator.
In the denominator. That's
So
right.
it's a lot of memorization.
It is. It really is. That's it. That is it. The key is remembering the rules, and if you can memorize the rules, then you're going to be okay. And you got the luxury of online quiz. Yeah, yeah. There's a lot of rules here in this chapter. There's a lot of stuff. But again, if you know it's got a positive sign in front of it, it's going up top. If it's got a minus sign in front of it, it's going on the bottom. And you're always going to multiply together when you condense down. Either the positive things are multiplying together on top, the negative things are multiplying together on the bottom. You know that's always what's going to happen, because the logarithm rules, none of them change addition or subtraction back into addition or subtraction. It's always change it into division or change it into multiplication. So it's always multiply. The sign tells you where to multiply. Positive up top, bottom is negatives. Okay. So, all right. So that would be that version there. All right. Now let's jump into the next section and talk about solving some logarithmic and exponential equations. Did a little bit this with last week's stuff. This week it's going to kind of go back to that a little bit, but then get into more complicated ones that have the logarithms going on as well. So I'm going to solve logarithmic and exponential equations. Starting over on my letters here. Example A for that, we're just going to jump in and we're just going to solve. That's what our job is. So 2 log base 5 of x is equal to log base 5 of 9. So the first thing that you want to do is look at each side and decide, can I condense either side? Okay. So on this one, is that a possibility? Yeah. This side over here has got that 2 hanging out on the front. So I'm going to move that over here and pop it back up there as an exponent. This is different than what we had done last week, because last week we didn't have a log on this side. We had just a regular number, and then we could have divided by 2 to get rid of it out of that. So when there's another log over here, you got to look at that condensing idea. This is how you know when to do that. All right, now, common sense tells me that if they're both inside of a log base 5, then x squared has got to equal 9. It has to. Now, mathematically, you can't just drop off the log base 5s. There's some math that happens that causes that. And this goes back to what we used last week. It's called exponentiating. So what you're going to use is whatever the base of the log is, we're going to exponentiate each side with that. So 5 is the base, so we're going to make 5 the base of the exponent. And this goes back to that simplifying property from the first section that we talked about, that if the base is the same as the log, then these cancel each other out. And then that's how you get x squared is equal to 9. And then how do you solve that equation? Since there's no logs on it anymore, it's back to a regular math problem. Yeah, you just take the square root of both sides. And anytime you take the square root of a number, you've got to put the plus or minus in front of it. So the square root of 9 would be positive or negative 3. And this is where we have to check our solutions to make sure that they work. So we have two solutions. We have x equals positive 3 and x equals negative 3. What kind of numbers can we take the log of? Positive numbers. So we've got to make sure, if I go back to the original problem, that I'm taking the log of a positive number. If I plug in the positive 3, log 2 log base 5 of 3, it's not a pretty number, it's a decimal, but it is a positive number inside of the log. So we're keeping that one. But if I plug in negative 3, I end up taking the log of base 5 of negative 3, which is not possible. So we're going to throw that out. That's what's called an extraneous solution. So you just X it out. Don't have that one. 3 is the only solution to that problem out of that. So got to check them in the original problem to make sure you're not taking the log of a negative number or 0. Always have to be, when you plug them in, what you're taking the log of always has to be positive. Doesn't necessarily mean that your answers always have to be positive, because you may have like an expression inside the log that might have like 9 minus x or something like that. And if you put in a positive number there, it could be positive, it could be negative. But you could put in a negative number there and it would always be positive if it was 9 minus x. So you've got to be careful about your, when you plug it back in, checking those things. Let's look at another logarithmic equation. Log base 5 of x plus 6 plus log base 5 of x plus 2 is equal to 1. All right, so this one, you've got 2 logs on the same side and then a plain number on the other side. So on the left-hand side, it's pretty obvious we could condense that. And that becomes what? Multiplication. So it's going to be log base 5 of x plus 6 times x plus 2 is equal to 1. So all of this stuff is being multiplied together here. But let's go ahead and get rid of the log. How do we get rid of the log base 5? How do we get rid of it on example A? We make 5 the base of each side. And it's called exponentiate. So when I do that, this 5 and that log base 5 go away. And then on the right-hand side, I've got 5 raised to the first power. What's 5 to the first power? Yeah, it's just 5. So I've got this problem now to solve. So I'm going to have to multiply that out. X times x, x squared. 6x and 2x is 8x. 6 times 2 is 12. I'm just multiplying those two things together. And it ends up being a quadratic. And how do we solve quadratics? Get them equal to what? 0. So I'm going to move that 5 over there with that 12. Give me x squared plus 8x plus 7 is equal to 0. And then what are my options for solving that quadratic equation? Factoring would be an option. It does work on this one. What's another option that always works? Yeah, the quadratic formula is also an option. Either of those ways, it doesn't matter. I don't care which way you solve it. Once you get here, pick a way. I'm going to use factoring on this one because it works pretty easy. 7 and 1, add to be 8. So multiplying to be 7, adding to be 8. Be 7 and 1. So that gives me factors of x plus 7, x plus 1. And then, so my solutions are x equals negative 7 and x equals negative 1. Those are the possible solutions. I've got to go back and check those in the original problem to make sure I don't end up taking the log of a negative. So if I go back to the original problem, if I plug in negative 7, what's negative 7 plus 6? Negative 1. I don't have to go any further. I don't have to check anything else. I know that's out. But it's possible that the negative 1 doesn't work either. So I've got to check it anyway. So I'm going to go up here and check the negative 1. Negative 1 plus 6 is 5. That works. I can do that. Negative 1 plus 2 is 1. Hey, that works as well. So that works. I'm going to keep that one. And it gives me the right solution there. So again, you're going to always check. And there's a case where we had a negative answer, but we didn't throw it away. We ended up with, throwing one of our negative answers away, but not all of them. Okay? All right. Let's look at, let's see here. Natural log of x plus the natural log of x minus 4 equals the natural log of x plus 6. So this one has logs on both sides, and on the left side, we got some logs with addition between them. So we want to condense that down. And how do those condense together? Multiplying. So it's going to be natural log of x times x minus 4, and natural log of x plus 6. Common sense tells us that the natural logs are going to go away. The math that makes that happen is, what's the base of natural log? It's really log base what? E. Okay? So to get rid of a natural log, you're going to exponentiate with an E. Those cancel each other out and leave us x times x minus 4 equals x plus 6. Distribute. X squared minus 4x x plus 6. And now what? Subtract the 6 and subtract x as well, right? Because I got to get it equal to 0. It'll be x squared minus 5x minus 6 equals 0. And then you're going to solve it either using quadratic formula or factoring. Both would work well on this one. I'm going to do factoring because it's -6 had to be -5. -6 and 1. So x minus 6 plus 1. So x equals 6. X equals -1. Those are our possible solutions. Go back and to the original problem and we check those. I think -1 it's pretty suspicious because it's negative, and right off the bat when I go into that first term, the natural log of -1, that's the log of a negative. I can't do that. That's not possible, so I'll mark that one out. Now I'm going to check the 6, make sure it works. 6 minus 4 is 2. 6 plus 6 is 12. So I end up with a log of positives there. So I'm pretty sure that that's correct. All right. So we've condensed a few here and gotten rid of the logarithms out of that. Nothing too strenuous on these yet. And so let's look at what I think are the tougher problems for the next 1, 2, 3 examples here, and then we'll get the application problems in. So it looks like we're going to get all 3 sections done tonight, which is great. That frees us up there that last week. All right, so let's look at some exponential problems. We're still just solving. That's our thing. So this is an exponential problem because it doesn't have logarithms in the original problem. 2 to the x is equal to 5. Okay, so 2 to the x is equal to 5. Doesn't have any logarithms in it, and the bases are not the same. Okay, last week we had problems like this that were 2 to the x is equal to 16. And what we tried to do was get the 16 to be 2 to the 4th power. And then that gave us x equals 4. We just automatically got that. But today, the bases are not going to be, you can't make the base of a 5 into like 2 to a power or to a nice power and be 2 to the, 2 point something. Bunch of decimals there. So we're going to solve this using logarithms. Exponential problems we're going to solve using logarithms. So what we want to do is try to make sure we're at the smallest base possible. So base of a 2, that's, you can't break that down any further, so I'm going to stick with that. And then we want to get rid of that base. So what log base would get rid of a base of 2? Log base 2 of 2 to the x. And if I do something to the left side of an equation, I have to do the exact same thing to the right side. And that goes back to one of those properties that we talked about at the beginning, that if we have log with the same base of the base, they cancel each other out and get a 1, right? So what happens there with this problem is these log bases, that cancels out the log base 2 and leaves just x. And on the right-hand side, we get log base 2 of 5, which is just a number. So let's find the approximation for that number. So with our graphing calculator, we're going to figure out the log base 5 or log base 2 of 5. So I'm going to hit math, and then I'm going to log base, which I just press the up arrow because it's down at the bottom. So log base, and then 2 of 5. And let's go 3 decimal places. So 2.322. That'd be what? And we have found the solution to that. So using the log to cancel out the base, we can solve these problems. Let's try this one. 8 times 3 to the x is equal to 5. This one's a little bit different than example D, but not too bad, with the fact that we have a got this number 8 in front of it. What's going on between the 8 and the part that has the exponent in it? They're multiplying, right? So can I get rid of the 8 using what operation? Think about it like this. If I had 8y is equal to 5, how would I get y by itself? Divide by 8. Yeah, it's the same idea. We're trying to get this dude by itself. That's what we're trying to do. Because if we can get that isolated, we know how we can take a logarithm and get rid of some stuff. So I'm going to divide both sides by 8. And I end up with just a nice looking fraction over there. 5/8. And then I take that and I say, okay, well, I got a log base 3. I really can't do anything to break down a 3. And I definitely cannot turn 5/8 into 3 to a power. If that were a 9 over there, I could turn that into 3 squared, and I got an easy equation to do. Or if it was 27, that's 3 cubed. But it's not. It's 5/8. So I can't do it that way. So I'm thinking, okay, I got to get rid of this 3. So I'm going to use a log base what? Log base 3. And whatever I do to one side of the problem, I got to do to the other side. So I'm taking the log base 3 of both sides of the equation, and they're canceling out. And there's x. And then log base 3 of 5/8. We can get the decimal approximation for that. Math, log base 3 of 5 divided by 8. Yeah. Negative 0.428 if we go 3 decimal places. So not too bad, but not, just again, it's just knowing, hey, I can't turn that into something. Let's look. Lied to you. We're going to do 2 more examples in this section. Let's try something like this. 2 to the x minus 1 equals 3 to the x. Try something easy before we get to one that's really kind of more difficult. All right. This one is a little different because what's different about this one compared to the last few that we've done? They both got exponents with variables in them. Okay. So which base do you try to cancel out? Well, that's the thing. Which one's harder, log base 2 or log base 3? You don't really know. They're both about the same, right? So you can't really just cancel out one of the bases. So what we have to do is use a common log to do this. So we're going to use natural log. You could use log base 10 if you wanted to. Our textbook tends to use natural log the most, so I'm going to use that one. And that it's shorter to write, so it's even better. Okay, so what we're going to do is we're going to take the natural log of each side. What that allows us to do then is get that variable, that exponent, down to the front using those properties. So we're going to have x minus 1 times the natural log of 2 is equals x times the natural log of 3. Okay. So now the next step is probably the trickiest one. Okay, maybe the second trickiest in this problem. Log base 2, natural log of 2. What is natural log of 2? Natural log of 2. It's that number. But the big picture is it's just a number. It's just like there was a 14 sitting there beside of it. But it's just this ugly decimal number. Natural log of 2 is just shorthand for writing that big long decimal. Okay? So what we're going to do is if this were x minus 1 and it had a 7 right there, what would you do to that with that 7 and the x minus 1? Distribute. That's what we're going to do with the natural log of 2. We're going to distribute this stuff to both terms. So that's going to give us x natural log of 2 minus 1 natural log of 2. It's still equal to x natural log of 3. Natural logs are getting sloppier as we go. All right. Now, which ones of those three things that are in that line, which two are like terms? What's it mean? That's a good question. What does it mean to be like terms? In an algebraic expression, let's say, for example, we had that problem, x minus 1, 7 in parentheses, and on the other side we had 5x. And we did the math that you guys said we would have done. We'd have distributed this 7x minus 7 equals 5x. Which of those would be like terms? Because they both have what? X's. So on our problem, it's a little more complex because it's got the natural logs in it. But the big picture is, hey, this piece right here is a like term with that piece over there. So if I get them on the same side, that kind of makes sense to have them together, right? So that's what I'm going to do. I'm going to subtract the x natural log of 2 from both sides. And the big difference is I can't go ahead and do that math for natural log of 2, taking that away from natural log of 3. I've got to just write it out. Negative 1 natural log of 2 is equal to x natural log of 3 minus x natural log of 2. Now, I told you that the distributive property was the second trickiest part of this problem. Here's the trickiest part of this problem. What do these two have in common? Yeah, they both are natural logs, but this is natural log of 3. This is natural log of 2. Those are two different numbers, right? So just x is the only thing that's really common between these two. So we're going to factor out an x because that's a GCF, right? If I factor out an x, that's going to give me natural log of 3 minus natural log of 2 is equal to negative 1 natural log of 2. Now, big picture, what's this stuff in parentheses? It's natural log of 3 minus natural log of 2. But what is that? It's just a weird decimal number is what that represents, right? So we have x times a number. How do we get rid of that number? Yeah, that's exactly it. So the opposite of multiplication would be division. So we're going to divide both sides by this weird number that's there. It's just a weird looking number, but it's a number. So I'm going to divide both sides by natural log of 3 minus natural log of 2. natural log of 3 minus natural log of 2. On the right-hand side, they cancel each other out. That's what I wanted to happen. So I got x left. On the left-hand side, I got negative natural log of 2 over natural log of 3 minus natural log of 2, which we know is just a number divided by a number. And we can get a decimal approximation for that, which is what we want to do. So x is approximately whatever that is. So I'm going to take negative 1 natural log of 2, close the parentheses, divided by parentheses natural log of 3 minus natural log of 2. Close those parentheses up. And I may wish that I had, I do wish I did that. Let me start over. So I'm going to do parentheses, negative 1, natural log of 2. So that's the numerator, divided by parentheses, natural log of 3, close parentheses, minus natural log of 2. Close those parentheses up. There we have, we're going 3 decimal places, so that'd be negative 1.7095. The 5 makes the 9 go up, and the 9 makes, so that makes that a negative 1.710. Is it okay to have a negative in the answer for these? Why? What's the, you had a 50-50 shot. That's pretty good. So what has to be in the problem for a negative to be an issue? In the original problem, has to have what in it? Log. Did our original problem have logs in it? No, we put logs in it to solve it. But the original problem was just this stuff with exponents. It was an exponential. So it's not an issue. You can check the answer by plugging that into x and seeing if left side equals the right side. It gets really, really close if you use the decimal form of that. But it doesn't throw it out if it's negative on this one because the logs weren't part of the original problem. We used them to solve. So that's the reason why. Okay. All right, let's look at one more for this section. Let's do one that's a little tougher because that one wasn't hard enough, right? But if you'll look at the skills that we used on that one, this one can be done in a similar way. It just takes a little longer. So this one got exponents on both sides that have variables in them, and the bases are not the same and can't be made the same. 5 and 3, both prime numbers, can't be broken down to be the same base. So this is where I know, hey, I can't use a log base 5 because it doesn't get rid of the 3 as the base. It only gets rid of one of them. So I can't use a log base 3 because it doesn't get rid of the 5. So this is where I know to use the natural log out of that because the bases are different and both of them have exponents with variables. So I'm going to use the natural log of each side. So natural log of 5, x minus 2, natural log of 3, 3x plus 2. Bring that exponent down. That's the whole point in doing that. So you end up with x minus 2 times the natural log of 5, and then 3x plus 2 times the natural log of 3. And then what did we do at this step on the last problem? We distributed, okay? So that's going to be x natural log of 5 minus 2 natural log of 5. It's going to be 3x natural log of 3 plus 2 natural log of 3. All right, so this one has more terms, but the same idea out of this. Well, my students have been asking me lately in Algebra 2 at high school because we're getting into some harder stuff here toward the end of the semester. They're like, how do you just know how to do this stuff? And I'm like, well, how does a mechanic know how to work on the car? Years of practice. That's it. And so knowing all of these things, you know, like, how do I know to do this? Well, let's take the experience that we just gained from the previous example and figure out what to put together here. So what do we put together on this one? Like term. So what is a like term with this piece? Yeah, so we need those on the same side. What's a like term with this guy? That other one there. So we need those two on the same side. So I'm going to move more than one thing at a time, just because I know I can do that. I know what goes together. I know that this needs to go over there with that other one. So I'm going to subtract it. No, it does not matter which side you go to. You pick whichever way you want to. It'll get the same answer. And then I'm going to do 2 natural log of 5 plus 2 natural log of 5. So that's going to give me x natural log of 5 minus 3x natural log of 3 is equal to 2 natural log of 3 plus 2 natural log of 5. So now I have all the x stuff on one side and all the non-x stuff on the other side. So I'm going to mark out the stuff that canceled so that it looks a little bit better. And again, it really doesn't matter what order, you know, if you have, you know, the 3x minus 3x natural log of 3 minus x natural log of 5, and then on the other side you got negative 2 natural log of 5 minus 2 natural log of 3. It's the same, okay? It'll end up being the same at the end, all right? Now, what did we learn from our previous example about what to do next? Remember, what is this? All this stuff on that side with the 2 natural log of 3 and the 2 natural log of 5. You know, just numbers, right? Just adding numbers together there. They're decimals of some sort. We'll get that in a little while. But that's just a number. So this is all numbers over here. This is some sort of stuff with x. Both of them have x's though, right? So what can I pull out of both of them? X. So if I pull the x out, that's going to give me natural log of 5 minus 3 natural log of 3. 2 natural log 3 plus 2 log 5. Now, what do we know about this stuff in parentheses here? No, it's just numbers. It's natural logs, but it's just numbers. So we've got x times a number is equal to a number. So what do we do to get x by itself? Divide by this weird looking number over here on the left. So if I divide a natural log of 5 minus 3 natural log of 3, natural log of 5 minus 3 natural log of 3, this side cancels, and the right hand side, you get this weird looking ugly fraction, 2 natural log of 3 plus 2 natural log of 5 over natural log of 5 minus 3 natural log of 3. That's ugly. Gosh, it's homemade soap. As my mom used to say. Y'all ever seen homemade soap? Y'all may be too young. I had some grandparents who used to make homemade lye soap, and they didn't have like molds and stuff. They just kind of wadded it together, and it was just weird looking shapes, and it wasn't pretty. And she'd say something, that's ugly. It's homemade soap, and so I've always loved that expression. All right, so now we're going to get the decimal approximation for that. So parentheses around the top. So we got 2 natural log of 3 plus 2 natural log of 5. So 2 natural log of 3 plus 2 natural log of 5. Close parentheses. Divided by parentheses. And then the bottom part is natural log of 5 minus 3, natural log of 3. Natural log of 5 minus 3, natural log of 3. Enter. 3 decimal places, negative 3.212. You would be surprised how many people that I've had over the years that could do all of this and they get the right exact answer and mess up the decimal because they would forget a parentheses or they wouldn't close a parenthesis. Like that, the most common mistake is when you type in 2 natural log of 3, not closing the parenthesis after that 3 and putting the 2 natural log of 5 on the inside. That's a common mistake on the calculator when you're trying to get it to evaluate that. So I've seen a lot of people that like they'd miss it on the test or something, and they'd come up and ask afterwards, and they'd say, "I did it," and you look at it and you're like, "Well, that's the right exact answer. Your decimal was wrong," and the decimal was the multiple choice version of it, and they didn't get the decimal right, but they had the exact answer right because they couldn't type it in the calculator correctly. So be very, very careful. Extra parentheses usually don't mess things up. Not enough parentheses always mess things up. Okay, so be careful of that. Those are as hard as they get. They don't get any harder than that. Did you get it? You're practicing.
Look at the wheel, I gotta get the parentheses.
Yes, yeah. Don't forget the parentheses. And, it might help if I write it in there that there's a parenthesis here, 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 and here, and then another one, and then another one, and then a last one. So all of those parentheses have to be in there in the calculator for it to work. If it's not, it doesn't get you the right answer at all. And depending on which one you left out, what answer you'll get, because it never comes out the same. Okay? All right, so they really don't get any harder than that as far as the logarithmic and exponential equations. Those are the toughest ones. So let's do some financial math, which is one of my favorite things, because it's an application that actually makes sense. A lot of times we make up this application stuff for you guys to do in math classes, and it really isn't something that you'll ever do. But this is actually something that you can use. So this is 6-7 financial models is what it's called. These equations that we'll solve in here are not nearly as tough as the ones that we just did. So, but this seems to make sense to folks because it's things that you compound interest, something that you encounter in life. The formula for compound interest is P parentheses 1 plus R over N, close parentheses, to the N times T. And A is account worth. P is your principal investment or deposit. R is your interest rate. N is the number of times compounded in a year. Compounded has a U in it. Compounded yearly. And then T is time in years. So if you open up a regular savings account down here at the bank, this is how interest is calculated. If you put a deposit in and just leave it there, you don't put anything else in it, it's going to compound interest. And depending on what bank you're with and what kind of account it is, how often it compounds each year, and what your interest rate would be. Okay, so if you're going into a cash deposit, a CD, you lock your money in there for a certain amount of time, and the interest rate is usually higher because you locked your money in. You can't get it out. They probably make you pay a penalty if you want to withdraw your money. But with this, we're going to put all this stuff in here. We're going to be able to calculate that, or we're going to be able to work backwards and solve for how long it'll take to get a certain amount. That's kind of our goal here. So let's take an example. So let's say if you invest $1,500 at some bank that's drawing 2.5% interest. I don't know if a bank does that around here, but they might have one. 2.5% compounded quarterly, which is pretty common. And you leave it there for 5 years. Let's say, you had an uncle pass away or something, and they left you $1,500. And you said, well, it's found money. I'm just going to put it away, let it draw some interest for a few years. And then 5 years later, he said, that money's sitting there. Let's go see if we got enough to maybe add to our vacation time. So what is the account worth? So this is a straightforward plug it in and work it out. So we're looking for account worth. We have a principal investment. We know the interest rate and how many times it compounds per year. We know everything that's on the right side of our formula. Our principal investment is the $1,500. The interest rate is 2.5%. So as a decimal, what's 2.5%? 0.25. If it compounds quarterly, how many times is that in a year? 4 times. Quarterly is 4 times. Monthly would be 12 times. Weekly is 52. If you did semi-annually, that'd be twice. Out of that, bi-monthly would be 6 times. Those are common words that are used here. Daily would be 365 in the bank. They don't account for leap years in the bank. Out of that. So the N is 4. The time is 5 years. Okay. So all this problem is just plug it in, crank out the answer. Okay. So I'm just going to get my calculator out and I'm going to type that in. 1,500 parentheses 1 plus 0.025 divided by 4. Close the parentheses. Caret symbol to get the exponent, and then it's 5 or 4 times 5, which would be, you could work that out and you could put 20 up there if you wanted to. But $1,699, and the bank's going to keep the extra change there. They're not going to round up. They're going to keep that amount and just give you 6 cents out of that. So $1,699.06. That is the account worth after 5 years. So in 5 years, we gained almost $200 without doing anything. Hopefully, we could put some more money into that account with it and draw some more interest out of that. But that's the way of doing that. So that was a straightforward work out what the account is worth kind of problem. Let's get to one that's more college algebra speed. So how long should we leave $1,500 in an account drawing 1.5% quarterly to have a total of $2,500. So not quite doubling our money, but how long should we leave that money there so that when we go to withdraw it, we're withdrawing $2,500 out of that, which would be a nice little few days on the beach. That. So again, our formula, principal 1 plus the interest rate over how many times a year raised to the n times t. So there's our formula that we need. Let's plug in the stuff we know. We know what we want the account to be worth. The account needs to be worth $2,500, so that goes over there. the amount we're putting into the account and just leaving alone. We're not putting anything else into it after the fact. We're just going to say $1,500. We're going to leave it laying. And then the interest rate, 0.15. Quarterly is 4 times a year. And then we don't know the time. So T is our exponent variable out of that. So this is what puts it in chapter 6 with what we've been talking about. So this is what makes it that kind of problem. All right. So let's work on undoing this problem so that we can get T by itself. So what's going on between all of this stuff and the 1,500? And how could I get rid of the 1,500 and move it over there with 2,500? Just divide. Yeah, that's an easy thing to do. So that's what we're going to do. We're going to divide by 1,500. And I'm going to reduce that down. 25 over 15 would be 5 over 3. And I'm just going to leave it as that instead of getting a decimal. And then 1 plus 0.015 over 4, 4t. Now, this is just a number, right? This 1 plus that would be a decimal. And I just want to write that whole decimal down out of that. So how could I get this t or this exponent here down out of the exponent using what we've talked about tonight? Absolutely. Because the bases are not the same on both sides, right? I got a 5/3 on one side, and definitely that stuff right there is not a 5/3. It's something else. Okay? So we got different bases. So what did we use when the bases were different on each side? We used a natural log out of that. So if I take the natural log of each side, that'll allow me to take the 4t down, and I'll get natural log of that junk, 1 plus 0.015 over 4. And then on this side, I got natural log of 5/3. And I want to get t by itself. So what's going on between 4t and this natural log stuff? They're multiplying all that stuff. So to undo that, I need to divide by what? Everything except what? Just t. I can actually divide by the 4 with that because it's just a number. Just like this stuff inside the natural log is just a number. So if I divide both sides by that mess, that's going to cancel out everything except for t. So I need to work that out. So I'm going to do natural log of 5 divided by 3 divided by, and then I need to open up a set of parentheses, 4 natural log 1 plus 0.015 divided by 4. Close up those parentheses. Did y'all get 34? No, we may be able to go to the beach, but we're going to be old and wrinkly by the time we get there. Because it's going to take 34 years to get that $1,000 if we don't put any more money in there. 34.12 years. You don't have to. You can. If you did parentheses, natural log of 5 divided by 3, and then close that parenthesis, that signifies that's the numerator. You're going to still get the same answer. Should. Let's check and make sure. Natural log 1 plus 0.015 divided by 4. So being able to find the time that it takes to make an account worth a certain amount is what we're using that for. And it's just using, the experience that we have from other equations to get us there. Let's look at continuous interest. Continuous interest is something you see and you hear talked about, but you never find locally. Continuous interest, you might be able, with today's online banking and all that stuff, you might be able to find a bank online that does continuous interest, but there are very few local banks that will do continuous interest. What that means is they're constantly, every millisecond, dumping your interest back into your account. It's not every 3 months. Most of them around here, if you do a savings account, it's once a quarter, they're putting your interest back in, and then your interest builds, your account builds from there. Continuous interest has this formula, and I always call it the PERT formula, P-E to the R-T. P is still your principal. The R is your interest rate. T is still time in years. The E is the exponential number, that 2.71 blah 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 stuff. So that all that stuff is, that E is that number that is like the log base E type thing. Okay, so continuous interest, you might see that in a larger account type place, which is why a national bank would be what you would think you would see that in, because they deal with larger investments. Let's say we invest my teacher salary. I'm glad somebody laughed. At 2.75% continuously. For, let's see, I plan on teaching for 14 more years. So, well, take that back. Let's do 17 more years. That's probably how long it'll take. I'm not sure. Yet to be determined how smart the youngest one is. He hasn't started school yet. So we'll see how long it takes him to graduate from college. If he's like me, he may never graduate. My dad always said, you've been to school long enough to be a doctor, but you're not. You're right, I'm not. Nor would I ever want to be. All right, so we got an investment, we got an interest rate, we got a time, we got all the information we need to just plug it in and get the account worth. So we're just taking that formula, the PERT formula. That's the way I remember that. Just memorize PERT. There used to be a shampoo called that. I don't know if they still, do they still make it?
Green.
Yeah, the green. Yeah, I remember. PERT Plus. Yeah, I remember that. So 300,000 is our P value, our principal investment. The interest rate, we're going to convert that to a decimal, 0.275, and our time is 17 years. So we're going to see how much I got to retire on after that time. Okay, so 300,000. 300,000 times E. To get the E, you need to hit second and natural log. Second natural log gets you the E, and it'll go ahead and put the thing there for your exponent. Second natural log, which is right beside the 4. And then we're going to put in 0.0275 times 17. And after 17 years, I can withdraw $478,799.76. Which will probably just barely pay for the insurance. So The nurses are taking care of me in the nursing home. Oh, that's where your money's coming from. All right. Last one. We're done for the night. How long does it take to triple an investment with 2.75% continuous interest? This one's it's a little tricky, but once you see the trick, it's not so tricky anymore. How long does it take to triple an investment? But they don't tell you how much my investment is. Does it matter how much my investment is in terms of how long it takes to triple it? If I put in $100 and I triple it, I'll withdraw how much at the end? 300, right? If I invest $1,000 and I triple it, still 3,000 at the end, right? It's the same ratio between the two. So if I'm going to pick my investment to work this problem with, what would be the easiest number to invest? $1. Exactly. That's the easiest thing. If I can invest $1, the greatest bid ever, if you're ever on Price is Right, make sure you bid $1 just to say you've done it. If I invest, my principal investment is $1, then I know that when I triple it, I'm gonna have $3, right? That's the easiest math to do. If they said something about doubling it, my account worth at the end would be $2, right? If they said quadruple it, my account worth at the end would be $4. So make it easy on yourself and pick $1 for your investment. If you wanted to pick $572.16, you can, but it's like you got to do the math and multiply it out. I'm picking $1 because it's easy. All right. So when I set up that, it says continuous interest. So I know I'm using the PERT formula. Okay, A equals P e to the RT. And I'm plugging in the stuff that I made up, the triple in investment. The $3 is equal to $1 e to the 0.0275 t. How do you get rid of that 1? Divide. If I divide by 1, I just get 3. E to 0.270275. All right, got an E as the base, and got a T in the exponent. So how do I get rid of that? If I do the natural log of both sides, what happens on the right-hand side? And what happens to the natural log of E? Go back to your properties from the beginning. One of the rarely used. The natural log of E becomes 1. So on our problem, this really just cancels itself out. You get 0.275 t is equal to the natural log of 3. And what do we know the natural log of 3 is big picture wise? Just a number. So I'm going to divide by that natural log of 3 by 0.275. So I'm going to do natural log of 3. Divide that by 0.0275. And it only takes me almost 40 years at that interest rate. So If you invested $1,000, you'd get 3,000. With any number, it doesn't matter what our investment is. If we invest $1 million in 40 years, we now have tripled that to $3 million. I mean, if you got $1 million laying around, probably doing around.
No, I don't.
I don't either. So I don't know if I've got an extra dollar laying around. Anyway, but it's 39.95. 39 years to triple our investment. If we had to double the investment, we'd take a natural log of 2 divided by 8 and see how long that would take. Which I'm curious. Natural log of 2 divided by 0.0275. It'd only take 25 years to double, which is a little more reasonable. I'm not sure I'll live another 40. Maybe not 25, but close. With a good chance of that, out of that. So if the interest rate goes up, then obviously that time goes down, is what happens there. All right, so finishing up chapter 6 there. And so things going on this week. Quizzes for those 3 sections, and then I'll send out the review for the chapter 6 test as well. And then let's see, we have today's the 11th, November 18th. We got chapter 12 and 25th, which is the Monday before Thanksgiving, and then we got that week break in there. So these 3 quizzes, and then the chapter 6 test. I'll send out a review for that, and then the test will be posted as well. So you got 3 quizzes and the chapter 6 test. I will put the due date for the chapter 6 test, not this coming Monday, but the Monday before Thanksgiving. So that gives you time to get these 3 quizzes out of the way and kind of breathe a little bit and study a little bit and then take that test. We will meet next week. We'll get into chapter 12 and we go from there. So that's the plan of attack this week. Y'all be safe going home. Stay warm.